Okay, perfect. Hello, students. How are you doing? I think very well as we were speaking before I start recording. Okay, just 1 second. I need to leave for. I mean, for 1 second, I forgot one thing, but um, please keep in mind if you have any questions of the content of the subject, so you can ask me. Okay, I will come in 1 second. Okay, perfect. Um, cool. Do you have any questions? No? No? Okay. Do you have a, I have a question for you. Did you see Alejandro's class about the quantum Fourier transform?
Yes.
Yes, good. The rest?
Yes.
Yes, cool. Francisco and Marta as well, yes?
Yes.
Okay, so what is the quantum Fourier transform? What is the quantum Fourier transform doing? Please.
I can go. Transform from one space to another, from time space to frequency space
Mm-hmm.
in a summer.
Yeah, yeah, very cool. Okay, and an application, if you could say, I mean, this is the perfect answer, Marta. Thank you very much. And perfectly. Now, if we would need to translate into quantum computing and any application of the quantum Fourier transform,
It helps to find periodicity of the functions, right?
okay, but I'm searching for another answer. I mean, it's fine. I mean, you know, and I would say I'm not expecting from you to reply what I want to hear, but I'm just guessing if you know or not. So, any other thing you would like to say?
Um, Differences in phase estimation like help with data, let's say, and I was looking at processing information like images and so on.
Yes, but why? I mean, this is the key fact. Yeah, it
Maybe
helps
because
to
of the
process
noise.
image. Sorry, Marta?
Maybe because of the noise.
No, no. I mean, the answer is based on the first reply that you gave me, Marta. No problem. I mean, no problem, but it's just in case. I mean, why it's able to help to process images, etc. Because it helps to change from a frequency to time period, and how this is translated into quantum computing, this enablement.
Because of the phase estimation.
No, phase estimation is another stuff. I mean, it's another fact. Phase estimation is one thing, and quantum Fourier transform is another. Okay, no worries. I mean, perfect. Thank you very much, all of you replying me. I'm going to start sharing my screen. I mean, you were all right, okay? And maybe you said the same and you're going to tell me, I, Alberto, you said that, etc. And I say yes. I mean, the Fourier transform, the classical Fourier transform, what it does is what you said. It sends from it translates, it's a projector, okay? It translates one wave function to the elemental frequencies wave functions. So you can decompose this is not a very complicated one, but very complicated wave function into the elemental wave function. So this really enables in electromagnetism and electrical waves, and even in the real life, to being able to know whether, for example, a bridge is going to be broken or not, right? Till here, you understand me and you go with me, right? The main fact of the Fourier transform is the decomposition in elementary frequencies, in the harmonic frequencies. Okay, this is the key fact of the Fourier transform. But the key fact of the quantum Fourier transform is what you said all, but in quantum computing is that it enables us to get the result of the eigenvalue of the function into the eigenstate, because remember, in quantum computing we are not measuring here. That it was related what you answered, Urbano, about the period, okay? But it's not guessing the period. It's that we can get the period, the eigenvalue, the solution of an algorithm. We can get the numbers, the coefficients that belong to the eigenvectors into the eigenvector itself, so we are enabled through quantum computing to compute the solution. I mean, the quantum Fourier transform, why it is very helpful in quantum computing, it's because we can change eigenvalue for eigenvector and eigenvector for eigenvalue. I mean, we can put the number, the information that is contained in the eigenvector into the eigenvalue and vice versa. And in quantum computing, we can only measure the probability of obtaining one eigenvector or another. That's why it's so important. Okay? Now, did you get my point of how I was saying no to your correct answers? But because the key fact of quantum Fourier transform is when I say eigenvector to eigenvalue and eigenvalue to eigenvector. Okay? Does this make sense to you? Do you understand this key idea?
Yes. Yes.
Cool. Perfect. Thank you. Then, if you allow me, let's go for the next one. Okay. There is a deliverable, okay, in this part. Okay. Before we go for the quantum phase estimation algorithm, that is the key part of this class today, we need to understand what the phase kickback effect is. I mean, I am following the old, I don't know if now it already has the same ones, I don't think so. Even I think they are deprecated, but I'm following the old, um, learning Qiskit learning documentation. Okay, and they call this quantum physics effect, that for me is intrinsical of quantum mechanics and is the main property for quantum algorithms. So why the reason why it's so powerful. But this is how Qiskit call it, and I call it the same phase kickback. Okay. Do you know what it is? Any idea? No? Okay, no problem at all. The phase kickback effect, okay? Let me read it because I don't want to say no in another way. Okay.
Isn't it the fact, Alberto, that another qubit is influenced by one qubit because this data is passed to the operator is its eigenvalue?
Yeah, correct. Exactly this, Marta.
That's why it's called kickback, no? Because it kickbacks.
Correct. Yeah. No, no, yeah, exactly. That's exactly what you said. For the rest, we have yeah, correct. I mean, perfectly. I mean, the phase kickback effect is the operation where when we apply a quantum operator, a matrix to two different eigenstates, to two different wave functions, to two different group of qubits, it changes the control qubit while it leaves the target qubit unchanged. What does it mean? It means that usually in the theoretical quantum algorithms, I need to do one step backwards. In my vocabulary, for me, there are at least two types of quantum algorithms. Okay? And when I say two types, it can be more. But there is one that is the supremum, and then in the other ones. The theoretical quantum algorithms, for me, in my vocabulary, the theoretical quantum algorithms are the quantum algorithms that are demonstrating theoretically that they have an advantage against their classical counterparts. Dodge's algorithm, Simon's algorithm, Grover's algorithm, quantum phase estimation algorithm, Shor's algorithm, HHL algorithm, etc. Okay, so the theoretical quantum algorithms, all of them are based in this effect to extract the solution. I mean, all of them are based in this effect to extract the solution of the phase kickback effect. Okay, and the phase kickback effect. Sorry. So all the theoretical. Then the other types of algorithms are, I don't know, any others. The optimization algorithm, the quantum machine learning algorithm, etc. Okay? Because there are multiple quantum algorithms. You can create yourself a quantum algorithm. But a theoretical quantum algorithm that is theoretically demonstrated that has an advantage against their classical counterparts are the only ones that like genius, or maybe you are a genius, and hopefully you are, and I would say I was your professor, but not that smart, are demonstrated that have a quantum advantage. Okay, the Shor algorithm to decrypt the keys, etc. Okay, so theoretical and then the rest. So all theoretical are based in this effect or the phase kickback effect. That means that while the target quantum operator is applied into two groups of qubits and the target qubit remains unchanged while the control qubit is changed. What does it mean? It means that usually all the theoretical algorithms start n qubits target wave function starts in 0. Then I will put something else, okay? Then we have a wave function. Then we have this. This now is the control qubit. Then we have this a bit longer. And then finally we have the same. Shit, sorry. And then here we have theta, for example, the finally wave function. And t, see, okay, yeah. Okay, here is m, sorry. M, t. And what is missing right here is this, the following is here we have U, for example, yeah, yeah. U operator applying 0 wave function. Then here we have, I don't know what operator you want, A. And finally, it's here, right? I don't remember, but now we need to apply the quantum Fourier theorem. QPE, Q if T to get the solution. Because all of this is processing in the eigenvalue, and at the end we need to apply the quantum Fourier transform. I think it's only in theta, not here. I think it's only in theta. I don't remember now, but we need to apply the quantum Fourier transform to pass all the operations that we did in the eigenvalue to the eigenstate so we can measure the solution. Okay, so this is the phase kickback effect. Okay, and that's why it's such important. Phase kickback. Okay, okay, now we see the theory. Perfect and perfectly answered. Marta, you said what I was expecting to be answered, so good. But now let's see how this is applied in the real world. Okay, as I told you, the phase kickback effect is the operation where a quantum operator applies to a target qubit and a control qubit, and the target qubit remained unchanged while the control qubit is changed. Okay, then imagine we have here the T gate. The T gate applied to the. Okay, one more thing. Maybe I'm going very fast or not. Please, as I cannot see you, if you have any answers or whatever, anything you need, please interrupt me and I will repeat it again or whatever, okay? I'm just maybe going fast because you told me you see quantum Fourier transform, etc., and you already have a certain level, a good level of quantum computing as you have, and that's why I'm going faster, okay? But please, in case not, just stop me, interrupt me, and I will repeat, explain anything you need, okay? What time is it? Okay, cool. Then the T gate. The T gate is putting well, in that case, a global phase to this eigenstate one. It's applying a global phase. Okay. One very important aspect. Quantum computing is only measuring relative phases. Quantum computing never measures global phases. Global phases is a factor common of something, okay? Is a factor common of something and only measures relative phases. What does it mean? Imagine a relative phase is the following. Imagine we have a wave function. One second. I'm going to put this so I can structure the information for all of you. I don't remember how to work. What a relative phase is? A relative phase and a global phase, I mean, we have a wave function like that where we have, for example, E to be 0 plus, this is a phase, right? I mean, if we would have here, for example, well, I need to include that. This is, I mean, all of this is a phase, but basically the imaginary number is the phase. This is the probability to get that number. So I need to include that. So we have both probabilities. In the same way, okay, we have a wave function like that, plus plus, and then we need to apply this for normalization factors. And here, instead of E, we have E piece. Right? So here we can extract a factor common of, do you see that? Or should I explain it in deep detail? Hmm. Do you see that?
Yes.
Yes.
Yeah, okay, awesome.
Yep.
You are so smart, very good. I mean, if you don't see, no problem, you are also smart, but I will explain it, no worries at all. But you see that, right? Okay,
Albert,
global phase, yes, sorry,
why is not the two above in the numerator in the green circle?
yes.
Why is not up instead of down? Because if you multiply the global phase with the relative phase, you have pi over 4.
No, it's not pi over 4 because it's exponent, so you need to sum up, not multiply it.
Okay.
Yes?
Ah, okay, I see it. And then another question.
Yeah.
When can we put the relative phase or global phase as a -1 in front of the state?
Repeat?
Sometimes we see the phase with a
Yes.
minus,
Yeah,
and
usually,
that gets me,
yes, usually, yeah.
that gets me confused.
Yeah, I mean the minus is because it's the time evolution operator of the Hamiltonian. I minus ITH. This is different. This is just a wave function. I just here want to explain you the I mean the difference between a global phase and a relative phase. So this is an imaginary example I provided to you so you can understand the difference between the both of them. What you are having in mind now and is confusing you is because this I minus ITH or I minus IHT, this is the time evolution operator. It's a quantum gate. Yes?
Mm, okay,
Do you get it?
I think so. But do you know when we sometimes we have the state 0 minus state 1?
No, but
So
this is another fact. Yeah, okay, but let me, sorry, let me just show you, okay, what I'm saying. So when you see it again, I will tell you. Oh, very good. It's not here. This is what I mean, okay? Too simple, but this is expressed like this, you see? Hmm? Because it's the time evolution. This. This is the operator. You see, this is an operator. This is a matrix. This is a
Mhm.
quantum operator. It is a matrix, and this is what I was meaning. That based on your last question, it's not what you were asking for, but this is what I wanted to tell you. That's why I show you right now, Marta. Okay, but tell me again now, coming back to your question because it's not this. Tell me what do you want to
We
ask.
see sometimes in classes before from modern
Yeah.
modules and stuff, we've seen that the phase comes as a minus sign in front of the whole state.
Yeah.
So the state 0
Hmm?
minus the state 1, for example. Why, when can we put that minus instead of like the exponential?
Mm. Mm, I mean, I think I'm okay. I think I'm not understanding your question, but I'm going to reply it. Okay?
Okay,
Based
I'll put it in the chat. Sometimes we see.
No, 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 no. I get it. I get it. But what I'm trying to say is, based on my experience, there is not a reason why you put plus or why you put minus. I mean, for example, now we have this gate, right? T gate, right? So now we have T gate, and the T gate is equal to 1, 0, 0, A, Y, P4, right? Is P4? Yeah, P4. So the dagger, for example, is 1, 0, 0, I minus Y, P4. So here is a minus, but there is, I mean, what I'm trying to say is, I'm understanding the words, etc., but I don't know where you want to go. You know what I mean? Like why sometimes are minus and why sometimes is plus. I mean, it really depends on the formulation itself. Usually
Yeah.
it's minus. Usually in everything in physics is I minus I. I mean, it's true, but I would say there is not a specific reason. You know what I mean? Like it really depends on what you want to do.
I think can I try to I think I maybe understood what you were asking, Marta. So
Mhm.
can you
Yeah,
show us that the other one, the one which is E minus I, in which you have the two states, the zero and plus, please, Alberto?
but this is also something different. I
No,
mean,
no, I mean I think it's the first slide right there. That is where you wrote, right?
yeah, okay, but this is the state minus as Urbano was saying, Marta.
No, no, but I think that what Marta was asking is that sometimes, for instance, let's say you correct me if I'm wrong, Marta, please. What I understood is that sometimes, let's say you have the state plus, which is 0 plus 1, and you have the state minus, which is 0 minus 1, right? And The question was when sometimes we have that minus and why sometimes we have that plus. Is that the question? Or I understood it wrong? Sorry.
No, it's just like when do we add phases with the exponential form and when can we use signs? Because, for example, in the Dutch
Okay, okay,
Jozef,
repeat, Marta.
Ah,
Now I understand your point. Repeat
yeah,
again this question, this perspective of the question. Repeat it again, please.
yes,
Well, repeat, please.
when can we express the relative for global phases with exponentials, like we just seen in like the slide one, and when can we express it with signs like the minus? And
But
in
in the
the
exponential, right? Or here?
no, just like here, there.
Here.
Yeah.
I think that's also exponential, right? Because
No, this is not exponential. No.
no, it's an exponential in the sense of you have a phase there that is
No.
e
Ah,
to
yeah.
minus I pi, and that you write that as a cosine and as a sine, right? You expand the exponential into cosines and sines, and depending on the angle, you get the minus or the plus. Is that the question, or I'm understanding
No,
wrong?
I think it's not the question. I mean,
Okay,
I think not, but
sorry.
you are also right, Urbano. Okay. I mean, this question can be answered in different ways. Of course, the reason why here is a minus
I think
can.
quantum computers will allow us.
Hello? Maybe something wrong, no problem. Here, I mean, the reason why here is a magnum is because of the sinus and the cosinus part, because it's a two qubit one. Well, in that case, shouldn't be, I don't think so. No, this is not minus, I mean, this is not sinus or cosinus, but it could be a to I pi. That's right. I mean, this could be. But I think your related, Marta, is I would open the mind, okay? My opinion is I would open the mind. I wouldn't state where we need to put minus when is this and we need to put plus when is this. It really depends on what you want to do. I mean, in this specific case, for example, okay, in this specific case, here we have a minus because these are the eigen. In fact, I have this here. Okay. In fact, I have this here. These are the eigenvectors of the. These are the eigenvectors of the X Pauli matrix. So if we do the X Pauli matrix and we get the eigenvectors and the eigenvalues, okay, we have the X Pauli matrix where we have this is position 0, this is position 1. If we apply the X over the position 0, the eigenvector, 1, 0, what we get is 1. So it's the bit flip matrix. Okay, but what are the eigenvalues and what are the eigenvectors? So if we do this is linear algebra, okay, if we do this, we get that the eigenvalues is plus 1 and minus 1. And if we then get the eigenvectors, we see that the eigenvectors for one is 1, 1, and for the other is 1 and minus 1. So we say, for the eigenvalue plus 1, then the eigenfunction, what we get is 1, the eigenvalue 1, we get 1, 1, zeta, blah, blah, and this is 0 plus 1, because this is the sum of 1, 0 plus 0, 1. So we get 1, 1. So that's why it's written like this, and this is plus. But if we go to the eigenvalue minus 1, we get this eigenvector, and this eigenvector is 1, 0 minus 0, 1, that in that case is 0 minus 1, and we get minus. Yes? And finalizing before I asking you whether it is your answer or not, one more comment is all quantum algorithms, when you have a quantum algorithm, all of them, you start applying gates, and then you need to do the opposite, always. Why? Because this is needed to get finally the solution. You need to undo the operations to get what you want to get. Because usually what is happening here is that you get here you get an operator, x for example, and this is the only operator that you get. And this is the only operator you want. This is like the pre-processing inside the quantum algorithm, inside the quantum circuit, and the pre-processing. Then you have the operator, but then you need to undo the pre-processing. So if you have such gates, where here t is plus, then the dagger that is needed in all quantum circuits, and you will see a lot of this, is minus. So answering finally, before I ask you whether it is answer or not, because we will continue to this answer. Answering that is, I wouldn't establish why here is minus or why here is 1. This is not, I would say, the basis to build upon all the rest. What I would say is stay open-minded, and the basis that you know is what you have, if it's dagger minus, etc. And based on that, do your mathematics, do your development, and you will see whether you need to put a minus or a plus. Does this make sense now, Marta? Is it clear or not?
Yes, more or less. I understand the convention and the algebra, like what you would just explain, Alberto. It's just like when we talk, for example, about phase kickback, we always
Mhm.
the minus. I'm going to like post a photo on the
Yes,
chat,
please.
and you can see on the far right at the bottom, you can see that -1 exponentiated to the function and the 2 qubits. But see that it's a -1. It's not like an exponential.
Where?
In the corner bottom
Here,
right, -1.
this one.
Yes, exactly.
But this is for parity purposes. This is included here for parity purposes. It is changing this part from here. The fx is taking out the fx from here for being parity. So if this is pair, the sign is going to be plus, and if it's not pair, the sign is going to be -1. But this is the translation from fx to a normal one.
So it has nothing to do with the face.
No,
Oh, okay.
no, it's something different here. I mean, Marta, if you want, I think, we can continue if you want, but I think I more or less get your
No, no,
point.
no. Yes, yes, yes.
But we
You
can
can.
take it offline if you agree, but
Yeah.
because I think I already answered. So answering really your questions, it really depends on the topic, you know? Here, for example, this is not anything related to the face at all. This is related because here what we have is a function and it's conjugate. And if we want to pass from here to here, we need to extract this as a parity rule. And this is just to say, this is just to tell the parity. For example, the sinus is a non-parity function, right? Because sinus of 1 is not equal to sinus of -1. But cosinus is a parity function because fx is equal to sinus is an imparity function, I think it was said, because fx is equal to minus f of, let me write it here. This specific example, imparity, okay, impar- I think it was like that. Maybe I'm confused, okay? This is theory and it takes longer for me, okay? But this is minus f the minus x. And this is sinus the minus p. P is equal of minus sinus the minus p. Okay? And this is right? Because this is p and this is 0. So 0 sinus is 1 and the other is -1, right? Or in that case is 0. So, okay. Minus p, because p is 0. This is 1 and this is also 1, but if without the sign, it would be -1. Do you see that? Or should I do that?
I see it.
You see? Everybody sees? Yeah? Ampere
Sure.
is the opposite. If x is equal to f minus x. And the example, for example, is x squared, because 2 squared is equal to -2 square. This is how plots are visualized, okay? So in that case, this specific case, it does not take into be anything about the phases. In fact, see that fx is inside the eigenstate. So it's a way of translating, not translating the eigenstate, but transforming the eigenstate, and is related to fx.
Okay. Thank you, Alberto. Thank you so much.
Do you understand now, Marta?
Yes, yes, much better. I
Okay.
don't know why I thought you could like there
I mean,
was like any exponential form that you could just put into a -1.
I don't like this expression, for example. It's not my style. I wouldn't do that like that. You know, this is correct. This picture is correct. And all of this is correct. But in my case, I wouldn't express that like that. Here this is correct. You have a target qubit, then you apply a quantum operator, applying the phase cubic, and then what you have is a target qubit, and then you have here, you manipulate initially because you want to get, and we are going to do exactly the same right here. Here we are going to do exactly the same, okay? But I wouldn't express that like that. In fact, I wouldn't express fx like that in this case for me. I don't like this way of expressing that and do this because this is an assumption that is easy. It's fine, but it's not trivial, I would say, right? And it leads to confusion. Maybe a lot of people does it. I don't like this. Right? In mathematics everybody has their own style. And maybe this is good, but for me I don't like it. Yes. So, in my understanding, Marta, it really depends the minus and the plus, etc. It really depends on the mathematics behind. As I said, I would state an open-minded and just do the mathematics, and there is no, for me, I don't like general rules. Just very few moments I put general rules. I prefer to do the mathematics, and that's it. For me, what I really like to show you and to learn to teach you is the basics, where the basics you can build and construct all the mathematics. But I see you put something not really here with the question, but could have written the state.
No, it was me. I was
Yes.
just expanding yeah, no,
Okay.
yeah, nothing,
You can express that
not
like
to the
that as
point.
well. You can express that like that as well. That's correct, Urbano. Yeah. Yeah. Okay.
Thank you both.
No, sure. Is it clear more or less now, Marta?
Yes, yes,
Yes.
much.
Okay. Okay, awesome. Then we finalize it and we could do it. Awesome. But all of this, as I said, is correct, but I don't like the way of that. I don't like the way how this is expressed. Okay, because I agree, this is FX, this is FX. Everything is correct, but I don't like how this step from here to here, I don't like it because I think it's not clear the mathematics that go behind. And one more thing, and the reason why it's not clear, it's because the reason why it's not clear, it's because here we need more context to understand what fx is. Because without this, we cannot establish that this is correct. But okay, but as I said, at least from my side, and I think Alejandro Rafa did the same, does this do the same. I really like to teach the basics, and from there on, you create the mathematics around there, but not general rules. Okay. So every moment has a different opinion, and in that case, this is a parity. So fx should be a parity function. That's why here is the conjugate. This is my opinion. I'm not sure, and I don't want to say this, but yeah. Okay, and it really depends. So the minus or something, it really depends. Okay. Anything else? No? Cool. I'm happy. I'm happy. I'm happy. Okay, then let's go for it. We have t, and this is the gate. So when we apply t over the state 0, we get nothing. And when we apply t over the state 1, we get, in this case, for just one qubit, for this just one qubit, we got this global phase. Okay? So we see here that it points out when we apply x, it points out to the number 1, right? And yeah, no, this is one second. Sorry, this is x, but let's apply t. No, sorry, no, this is correct. Okay, sorry. Now this is correct. I mean, we apply x, okay, over the state 0 because we need to put the state 1. I mean, we are going to do now this operation. First x, we have 1 qubit, then we apply x. Now we have qubit 1, right? And then now we will apply t. And what we will get, as this is a global phase, we will also get 1. Okay? We apply x, and then now we apply the t gate. No, but this is not correct. If we apply x and we apply t, we don't get anything. Where are we going to see something in the quantum computer? So it leaves a change when we have a global phase. In that case, we have a global phase, right? Because here we have a global phase. So we don't see anything. But when we have a relative phase, so we put 0, now we apply Hadamard. So now what we get is the plus, and then we apply t, where we finally get is this final eigenfunction when we have, and we have 0 plus e p4 by 1. Oh, sorry, here is a get. So as here we don't have a global phase, we have a relative phase. We have a relative phase. Here is where we get the plus and where we can see through quantum computing the difference, because this is a relative phase. The phase kickback effect, I mean, sorry, this is not related to phase kickback, sorry. This is the relative phase. This is the difference between global phase and relative phase. You tell me, Alberto, I want to see a minus instead of this, I want to see a minus. So what does it mean? Instead of this 0, if I put 1 at the beginning, now here I get 1, I'm going a bit quicker, okay, faster. So here what I get is minus. So if I apply t, what I'm going to get is the same, but with minus sign. And minus e. And the question here is, and I'm going to show you, okay, minus. The question here is, even if I put x, is this picture going to change or not? I mean, is the arrow go to change of place even if I put a x at the beginning of this minus? Is this minus going to be expressed here to change this plot, or is going to be the same plot? Who wants to talk? What do you think? Let's do a bet. I always like to do bets, and I didn't do last class. Urbano, what do you say? Yes or no? Does it change? Yes or no? I mean, and you need to say something. If you are wrong, say whatever you want. Maybe you will be right, maybe not. But just say something, please. Urbano?
I think it's going to change.
Yes. Marta?
Yes.
Yes. Raúl or Francisco? Who goes next? I don't know. Francisco?
I think so, yes.
Yes. Raúl?
I have to agree.
You have to agree. Oh, and I say no. Maybe I'm wrong. Maybe I'm wrong because now, yes, I'm wrong. And why it's changing? Okay, yes. Okay. I thought not. Okay, okay. Yeah, so very good. Why it's changing?
Because now you're acting on with the t on the minus stage, right? Not on the plus stage.
Yeah, I mean, this is the reason, but the reason why it's changing is because it's basically a system of references. Here is 1. Here is -1. plus 0 and minus 0. Well, it's not like that. I mean, it's different because here we have 0 and 1, but yeah. Correct, very good. So you with me. Oh, 1+ point for you. Good. In the subject. Hopefully I could do it, but not. Okay, cool. Yeah, I need to remember a bit of the block sphere in my case, for example. Because I was thinking that it was not going to change because if we put here a minus applying the T dagger rather than the T, it is going to change, but not. In that case, this is going to change. What it would not change is the real solution because this is the block, the state vector, but you will never be able to really get this solution from a real quantum computer because real quantum computer is only give you the counts. When you destroy the quantum measure, I mean, not destroy, but when you measure, you destroy the quantum effects, you get in a classical way, so it's good. So solutions like that will be all able into simulators. Okay? But good. Perfect. Students, awesome. You win me. I'm super happy. Then remember, global phases cannot be seen in a quantum computer. Relative phases, do. Okay? Now let's go to the phase kickback effect. Till now, no questions, right? No, in fact, you asked me the questions, you are contributing a lot, so I'm super happy. Okay, cool. Then control T gate. The control T gate is the one we have here. It's applying in two qubits, 0, 0, 0, 1, 1, 0, 1, 1. And it's applying into two qubits. We have here a two qubit gate, okay, 1, and then 0, 0, okay, 1 and plus. This is the Hadamard. So 1, this is normalization factor. In 1, 0, this is the target qubit. The first qubit is the target qubit, while the second qubit is the control qubit. No? Oh, yes. Sorry. Correct. Yep. I mean, here we have two different qubits, okay? We have the one that is the target qubit, and the second one is the control qubit, okay? Then, because we apply the Hadamard gate, okay? Then we have the one and the control qubit. We apply the control T gate, and what we see is that when we apply the control T gate over a target and a control qubit, we see that the target qubit leave unchanged while the control qubit is changed. Okay, let's see what's happening here. But if we put here a 0, it wouldn't change. But let's see what is here. Let's compose this state and we have this state. Okay, here is the opposite. Okay, remember, in that case we are switching it. This is the target qubit and this is the control qubit. Qubit 0 is the control qubit and qubit 1 is the target qubit. Okay? I think it's just like that. Correct. Yeah, I'm right. This is the target qubit and this is the control qubit. Qubit, but in that case, this is switched. Okay? Do you? Yeah, I mean, I should switch it. But the rest, or I should change that to be accordance. I need to change. Okay, let me note that. Mm, mm, mm. Sorry, students. I realize of that just to be to have coherence. No, yes, it is correct. I'm sorry, students. As I don't do, no, no, this is correct. I'm so sorry. I always have this problem. That's why I'm always super careful about it. No, no, this is correct. Why? Because this is the qubit 0 and this is the qubit 1. Why? I always forgot, but I always forget, but this is important. How you need to read everything is that this is qubit 0 and qubit 1. Why? Because if we should translate this from a binary to a decimal number, this would be the exponential 0 and it would be the exponential 1. Okay, so it's in order. This is qubit 0, this is qubit 0, and this is qubit 1, this is qubit 1. Okay? So here we have a control qubit and a target qubit, while the target qubit, as you can see, we can extract a factor by the control T gate. We can start a factor, common factor, and we extract the target qubit and change. The control qubit is changed by this. Okay, so control qubit 0, qubit 1, qubit 0, Hadamard, and we get the Hadamard, and we get this. Then we apply qubit 1, there's the bit flip, and we get the target qubit, okay? And now, when we apply the control T gate, what is happening? That the target qubit leaves unchanged, okay? Because no operation is affecting it, while the control qubit is changed. It has a relative phase from here of P4, from here to here, relative phase of P4. This is why it's plus P4. If it was minus P4, it would go the other way around. Maybe I'm not right as before, but yeah. Okay. So this is the phase kickback effect. Questions before we go for more examples? Nothing? Okay,
No.
cool. So this is the phase kickback. Then, as you can see, here we are not applying the control T gate, so nothing. We get the counts, 50%. And here, where we apply in the control T gate, it is not happening anything. What's the important fact here from this part of the class and this part of the lesson? One, real quantum computers do not measure relative phases, and I mean, real quantum computers do not measure phases. Okay, phases in general. Global phases are not taken into consideration in quantum computing, in quantum circuits, but relative phases are. But real quantum compute. So the two things that I want you to keep is one, real quantum computers are not measuring phases. They are measuring probabilities. That's why quantum Fourier transform is so important. Second, phase kickback effect is the fundamental, the building block of all theoretical quantum algorithms, and it remains on the way of applying a quantum operator to two gates, and while the target qubit remain unchanged, the control qubit changes. Okay? Questions? No? Cool. Then now go to the quantum phase estimation. Okay. This is the other Jupyter notebook I have. Do you want to do a break now of 5-10 minutes or should we continue? Up to you. No question? Should I continue then?
Yes. Sure.
Cool.
Yes, for me, we can continue.
I think this is the only, yes, cool. Okay. Then we got here now, one very important aspect, students. If you really want to do work in quantum computing, etc., my recommendation is once you finish the master, you take the exam of the certification of QCT2026. Do you know that it exists?
No.
Okay.
Yes.
And this is very important for everybody, okay? I haven't it yet, but I will do. Oh, withdrawn. I don't know what's happening. But well,
This is the old one. This is the
this is the old one.
old one.
0.2. That's right. Thank you. And what is the...
No.
Yeah, this one. Good. Thank you, Urbano. I mean, I have the older one. I mean, well, if you don't know, I'm telling you, in work, there are something that are called certifications that are, for example, there are in NVIDIA, Microsoft, Amazon, etc. And certifications are very difficult exams because you need more than 80% of 80% of success to pass the exam and to get the certification, and they are very, very difficult. I mean, for example, most of them now are done online, and you cannot even speak. You cannot have anything in the table. You need to do all of memory, all of these mathematics by memory. I mean, they are not easy at all. Honestly, I mean, all the certifications, I didn't much. I didn't do much, but just Amazon and yes, Amazon and quantum computing and Amazon quantum computing and Amazon infrastructure. And now I'm going to do NVIDIA infrastructure as well. And they are not easy. I mean, of course, you can pass the exam and you can with this master. You need to prepare it. I mean, this is exam you need to prepare, not just signing and going for it. You will do it. You need to prepare it. But certification at work are very important because it's something that the provider, the technology, gives you. It remains personal. It does not remain to the company. Usually, all companies pays for it, and it remains personal, meaning that if you leave the company, the certification is still with you, and it demonstrates that you know how to use the technology, and they are very important. Okay, so just letting you know, I will put that in the notes. So Kiskis had the certification, and for example, in my place, I will do it, but I really need to prepare the exam if I want to pass and not fail. So they are not easy. Okay, just letting you know this info. Did I copy it? Yeah. Okay. Let's go for it. Before I started explaining the quantum phase estimation algorithm. Just well, this is why I say that of the simplification is that I remember that, for example, now the sampler, the primitives are a state vector sampler or a state vector estimator. Before it would just was in previous version for Qiskit, it was just the sampler or the estimator. Sorry, and they are now different. And here we have the quantum Fourier transform. I just prepared it, okay? So this is encapsulated and we can use it. Okay, quantum phase estimation algorithm. Any one of you, and well, if you want to read and then say it, it's fine. But do you know anything about the quantum phase estimation algorithm? I think so, right? Because you saw it in the quantum algorithms class, right? Or if you could tell me, please. I don't remember.
Yes, we saw it in quantum algorithms.
Yeah, really? So do I need to explain it? Well, I will explain it, but very shortly. But thank you very much. I think it's Francisco. You reply Francisco, right?
Yes.
Good, good. I know the voice. Awesome. Then, if you saw it, what? So you know, if I'm correct, I'm correct. Sorry. So if you know, the quantum phase estimation algorithm, basically what it does is that it enables through the quantum circuit to extract the eigenvalue from a certain operator, meaning that the quantum phase estimation algorithm allows you to extract the eigenvalue of certain operator. For example, imagine that we have such operator. I'm going to put a 3 qubits matrix, okay? We have a 5, 0, 0, and I'm going to give it diagonalized already, diagonalized, okay? 0, e, pi, for example, and 0, 0, and what can I put here? And yeah, 1, 3, okay, so it's normalized. But I would put it here, but yeah, I'm stupid. Okay, in fact, I'm going to put it there. What I can put here, for example, minus. I'm going to put a minus for you, Marta. Okay, minus pi 4. What it means is that if I want to get, for example, 0, the eigenvalue, I mean, through the, sorry, mm, how I'm expressing right here. I want to use the same syntaxes. Correct this, okay? Okay. Then if I want to, I mean, applying the quantum phase estimation operator over 0, where I would get the solution is 5. We will see that, okay? Well, in that case, I will get 1. Okay, I'm not going to express that in such a way. I don't like it. Okay. What I'm saying is, if I want to get the state, imagine we have instead of qubit, a treated. Okay? Qubit, quantum bit, quantum treat, a Q treat. Instead of having a qubit, we have a Q treat. So if with the quantum phase estimation, what I would get is the phase, quantum phase estimation, the phase of the eigenvalue of the first one. That could be phase 1. Eigenvalue of the second. It means I would get pi. It's not that like that because we will see now the deviations, but in a high level. I mean, I just want to introduce you to quantum phase estimation. And if I would get of the in the Q treat the eigenvalue of the second eigenstate of the most excited state, I would get this phase of the eigenvalue. The quantum phase estimation is one theoretical is a theoretical quantum algorithm. It means that has a theoretical quantum advantage against their classical counterparts. It is a theoretical quantum algorithm that enables you to extract faster, in a quadratic speak, I think, but faster the phase of the eigenvalue of a certain operator in a certain matrix. Okay? Now we will see the clarifications. But this is what this is doing. And how this can help for business? What are the use cases? What are the problems it solves? For example, Google Maps. If we would, that you will see that later on in the master as a Hamiltonian, if we can express the different ways I can go from point A to point B, if I can express that in different way, how I can go from point A to point B in a matrix, thanks to the quantum phase estimation, I could get the solution faster than its classical counterpart. I could get the minimal path, the minimal way, how the fastest way to go from point A to point B. This is one use case. Another use case, ibuprofeno, drugs. How to get a drug similar to ibuprofeno. As you know, drugs are sorry, drugs no, but the interaction of a drug with a biological system is a Hamiltonian. It's a reaction. You can express that as a Hamiltonian. A Hamiltonian is a matrix. So if I can get the phase of the eigenvalue of this Hamiltonian, I would know what is the minimal eigenstate, the minimal eigenvalue of this Hamiltonian, and I could get with what is a similar drug for it. Another one, the portfolio optimization. As you will see, you can express the different stocks that you have in your portfolio with a risk associated to it in an optimization problem, and you could get them to quantum phase estimation how to get it. Is it useful? No. Why? We will see that. But why it's not useful? Because the circuit is so depth, It's so deep, but that deep is so very, very, very deep that we are not able to execute that in current quantum computers and in the following 5, 10, 15 years of quantum computer. Why? Because this is a theoretical quantum algorithm. It's good that you know the basis, but it's not a practical one. Why? Because of the depth of the circuits. The main problems of theoretical quantum algorithms are that they are not practical. They are not, I wouldn't say good, but they are not capable for NISQ devices. NISQ is noisy intermediate scale quantum computers. So they are not good enabled for NISQ devices. So quantum phase estimation is very good because you need to know the basis, you need to know the theoretical quantum algorithms, but really applied quantum computing will be seen in the two following subjects, A11 and A12, where A11 we will see gate model with KOA. There is another one, a quantum amplitude estimation, very similar to this one, but really applied to no, very similar to this one, but different. Quantum amplitude estimation, the variational quantum eigensolver, quantum machine learning, and then A12, adiabatic quantum computing. Okay, then to summarize, the quantum phase estimation algorithm allows you to extract through the phase kickback effect the phase of the eigenvalue of the desired eigenvector of a certain operator. It means that we have here all the control qubits, we have here the target qubit. If we want that if we want that the target qubit is in the state 0, for example, for this operator, we wouldn't get the eigenvalue, yes, but it would remain unchanged. But as we want here that the target qubit is in the state 1, so we put this in the state 1. Why I show you? Because what I mean is that preparing the target qubit in the eigenstate we want to extract the eigenvalue is the key fact. Then we apply the building block the building block of the then we apply the building block of the algorithm, that is this control operator gate, and then we are able to extract the eigenvalue. But first, we need to prepare the target qubit in the eigenstate we want to extract. Maybe it's two eigenstates, not just one, but we can prepare it in any of the eigenstates of the operator. And once we prepare the target qubit in the eigenstates of the operator, then we apply the building block, as I say, the control quantum, we apply the control quantum operator gate, and we extract finally the eigenvalue. So the phase of the eigenvalue. So here we have, so how the quantum phase estimation algorithm works is, here we have the control qubits. We initialize the system, meaning that we apply Hadamard to all of them. At the bottom, what we have is the target qubit, where we prepare the target qubit to be on one of the eigenstates of the phase of the eigenvalue we want to extract. Then we apply the control operator quantum gate. What is this? Why do we apply such times this operator, this gate? Because this is the precision of the solution. If we just apply one gate, we will just have precision, we will have precision 0. If we apply two gates, we have precision 1. If we apply, and so on and so forth. Okay? What it means is that as many gates, as many control operator gates we apply, the better the precision we will have. But more qubits will be required and more deep the circuit will be done. So that's why this quantum phase estimation algorithm is not useful. It's very, very powerful, but it's not useful. Okay? So as many gates we do the precision. No worries, because you will understand that, because the deliverable is related to that. What is the precision to get some certain phase, etc. Okay? So initialize, etc. And finally, in the control qubit, we apply the quantum Fourier transform dagger to put the solution of the phase to the eigenstate. So being able to measure it. So repeat again, summarizing at all. One, the quantum phase estimation algorithm allows you to extract the phase of an eigenvalue of a certain eigenvector of a certain operator. And the circuit works like control qubit, initializing the system, target qubit preparing in the desired eigenstate. We apply the control operator quantum gate. And finally, when we have everything, the target qubit remains unchanged, the control qubit change, so we apply the quantum Fourier transform dagger to send the information that we want to measure from the phase of the eigenstate to the phase of the eigenvalue, sorry, to the eigenstate itself. So we are able to measure in a real quantum computer. Questions?
Yes. So Alberto, so we need to know the eigenstate, right?
Yeah,
So
correct.
how is this that? Because I mean, I understand that this gives us the eigenvalues once we know the eigenstate, but do you how is this to know the eigenstate beforehand if you have a, let's say, a certain Hamiltonian or something like that?
Mhm. Very good point. I mean, the examples I'm going to show you is very simple. For business use cases, what you don't know is the eigenvalue, but you know the eigenstate because you build the Hamiltonian. What you want to know is the eigenvalue. That's why you apply this. That's why you apply this algorithm. Please, could you please remember me the your background, Urbano, so I can put you
I'm
an
a, I'm
example?
a, I'm a physicist. I'm a physicist. Okay.
Okay, then as a physicist, you know, okay, awesome. Then as a physicist, you know that you can build any Hamiltonian you want from any molecule, right?
Mm-hmm.
You know already know the Hamiltonian, you already know the matrix. The problem is that you don't know how to compute the matrix, the Hamiltonian to get the eigenvalue, correct?
Yes. Yes.
So here, I mean, with this explanation, I think I reply your answer, correct?
Okay. Yeah,
The
no, I was
thing
just wondering that if in general, I mean, for any operator,
is the same.
how is this to obtain the
I mean,
eigenstate before, I mean, the eigenstate of interest, right? Because it's not a, yeah.
It's always the same, Urbano. I mean, building the matrix, the operator, is the simplest part of any problem. The very difficult part in any area of business, of science, is the diagonalization part, solving the problem, getting the eigenvalues of the operator. But you already always know the operator and its eigenvectors.
Oh, I see. Thank you.
No, you're welcome. But do you get the point? I mean, I can put you more examples if you want.
Yeah, no, I get the point. I get the point. I
Okay,
mean,
cool.
the problem is diagonal. I mean, is getting the eigenvalue, which is equivalent to diagonalizing the matrix, right? So especially if it's
Correct.
big. Okay. Thank you.
Correct. And moreover, the quantum phase estimation, it has been theoretical demonstrated, but in practical, it hasn't been demonstrated. This is, for example, related to the question Marta asked me, like the previous lesson about is quantum computing well established? Not at all. I mean, this algorithm, for example, is theoretical demonstrating is having an advantage, but it hasn't been demonstrated in a real quantum computer. And maybe it's not that powerful, not only because of the huge amount number of qubits that are required, but also because the electromagnetic wave that helps in an scalable quantum computer is not here, so it's more costly, blah blah blah. I mean, one is
Mhm.
the theory and another is the real life. So it hasn't been, but theoretical here, even you can put, imagine that you have an operator, Urbano, where you haven't diagonalized it, so you don't put like the eigenvector, but you put the vector that is in the operator. It would also help here to get the eigenvalue,
I see.
so yeah,
Yeah. Thank you.
okay,
Thank you.
cool. For the rest, is it clear? Yes, cool, okay. Then, phase estimation algorithm. Do I need to explain that again? No, right? Because as I explained it before, it's fine, right? Or should I go quickly? No? Okay, well. I'm not going to explain it, just saying that This is algebra, and this is algebra, and this is sorry, this is algebra, and this is the diagonalization process of getting the eigenvectors and the eigenvalues of the Pauli matrix X, where we finally get that the eigenvalues is +1 and -1. The eigenvector of +1 is the plus wave function, and the eigenvector of the -1 eigenvalue is the minus function.
Yeah. Can I ask another question about? I think
Yeah,
this is
all you want.
this is a
Bueno.
great example because I think that, for instance, right? I think the way we normally do that in physics, in general, so many problems, is that you first find the eigenvalues, and then you use the eigenvalues to find the corresponding eigenvector, right? Like, so here, for instance, right, we find the eigenvectors doing the matrix. You do the matrix, whatever the matrix is minus lambda, the identity, and then you find the eigenvalues. And then once you have the eigenvalues, you substitute that into the matrix to find the eigenvectors, right?
Yeah, but this is the ideal world, Urbano. This is the fact. I mean, this is how to get it analytically, but there are a lot of operators where you cannot get the eigenvalues or even the eigenvectors in an analytical way. You need to get them from a computational standpoint.
Oh, no, I understand that. My point, I think, is the reason I was asking about the eigenvectors before is because normally when we do that, algebraically, we normally obtain the eigenvectors, the eigenvalues first. And
Yeah,
then we use that to get the eigenvectors. So that's why I was asking how easy it is to get the eigenvectors
yeah,
to
but
implement there to get the eigenvalues.
okay, I didn't express myself correctly, but I get your point. I mean, this is normally, I mean, this is no, this is not how normally is done. This
Hmm.
is usually done for teaching purposes and analytical way, like the theoretically and the ideal world. But this way of getting the eigenvalues is never used in the real life.
Yeah, no, I get that. But what I think I'm trying to say is that
Hmm?
we use the
This is the reason, I
eigenvalues.
mean, this is the reason why you asked before, because of this.
Yeah, this was the reason I was asking before,
Okay,
because
okay,
I
I
mean,
understand
my
now.
point, my point, I mean, in summary, I think my point is we use the eigenvalues to obtain the eigenvectors here, right? Okay, it doesn't matter how you calculate the eigenvalues, right? But what I mean is that in this case, we don't know the eigenvectors until the very end, correct? And
Yeah, correct.
and for the quantum phase estimation, your target state has to be prepared on the eigenvector, right?
It
So
doesn't.
I was just wondering how hard it is to get the eigenvector if you don't have the eigenvalues before, right? That's my point, I guess. I was
Yeah,
trying to.
yeah, I understand your point,
Yeah.
but I mean, again, no one uses this way of getting the eigenvectors and the eigenvalues for a
I
real problem.
I see.
I mean, this is just like in the school,
Yeah, yeah.
or in the academia. I mean, even in the academia, forgetting, as I said, theoretically advances, etc. This is school, academia, learning purposes. If you really go for a real business problem, for a real problem in business application, what I do, you will never use this method or this methodology. Even
Yeah,
if
I think I was just trying to understand how do you get the eigenvectors if you don't do it this way?
there are other ways, Urbano, to do it. I mean, I don't remember now. I mean, I don't remember now the names, but there are other ways of
No.
diagonalizing and etc. But even that, Urbano, people they do not care about eigenvectors. What they do care is about the eigenvalue, and with the eigenvalue, you can do everything.
Yeah, but I was just thinking that you need. I mean, we can take that offline later. I don't want to
Okay.
interrupt your class too much.
Okay,
Sorry.
yeah, because I think it's
Yeah,
more.
sorry.
I mean,
Yeah.
I'm trying to reply. I mean, completely we take offline. Just last comment from my side is I'm trying to reply you saying your question is not used in business, but you still, I mean, and it's not, I mean, and I'm not, please, I don't want to be, I don't want to express myself incorrectly. Of course, your question is very valuable. It just, I don't know the answer right now, but I maybe don't know, never, I don't know. I mean, but don't know the answer.
No,
Yeah, yeah, I mean, but what I'm trying to say is what is in business is done,
I
but
see.
it's a
I
good
see.
point.
No, and that's very valuable. Thank you. Yeah, I think I was just trying to understand how it's done. Yeah,
No,
that's
no,
it.
it's a good one.
Yeah,
I mean, we can take offline, as you said.
yeah.
Okay,
Thank you.
perfect.
Thank you. Sorry, buddy.
Cool. No, 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 sorry. I mean, for me, it's perfect. Thank you very much. The opposite. I mean, I'm super happy with all of you. Hopefully, you will come in all my classes because I'm super happy. You contribute a lot to ask questions, so I'm super happy. Okay, cool. Till now, cool. Okay. Okay, now you're going to see what we do have here is how to get the eigenvalue of a Pauli matrix X, okay, for the quantum phase estimation algorithm. I put this example because it's a very linear one, very simple, but being very honest, I don't like much because you need to imagine a lot of things, etc. So my recommendation is that you take a deep detail on that because I put it because just to get it. But let's go with a more real example, if you allow me, okay? Because here I'm just going to explain what is happening here, okay? Here we have the target qubit and the control qubit. We initialize the control qubit, we apply Hadamard, we initialize the circuit for the control qubit. Then we change the target qubit for our desired purpose. What it means is that we want the -1. That's why we apply a Hadamard and then a Z, because the Z changes the sign of the one. So we with these two operations we get this wave function, this eigenvector over here, and then we apply the quantum phase estimation algorithm. This simple this simple operator is the quantum phase estimation algorithm. Why? Because it's the CX. I mean, the operator we have is X. We're going to get the eigenvalue of this operator with this eigenvector. Yeah, it's two, like 2, 2, 2, 2. So we apply the quantum phase estimation algorithm from this eigenvector, and then we apply the inverse quantum Fourier transform. That for a single qubit, it can be said that the Hadamard is the quantum Fourier transform and the inverse quantum Fourier transform, both, because H is a quantum game because it's a dagger. H is equal to H dagger. Okay? And then if we measure this final qubit here, what we get is 0, 1. That is the expected outcome. Because we need to see have 0 and 1, okay? Qubit 0 and qubit 1. Qubit 0 Qubit 0 is the control qubit, is the expected one. So, or not, I'm correct. I'm so sorry, students. I always mix the order here. No, then this is not correct, I think. Let me see. Yes, this is not correct. Maybe it's correct, and because if I say this is correct. Now, okay, I'm just going to explain you this example in more detail because I don't want to get you confused as I explain it now. You understand this? Perfect. We go on. Then we have here the quantum phase estimation algorithm applied to the minus gate. Okay. So we have here the control qubit, we initialize the system. Then the next operation we are applying is obtaining the minus eigenvector, okay, the minus eigenvector. And then we apply the quantum phase estimation algorithm. So if we go here, we control qubit, H initialization, control qubit, H initialization, target qubit, prepare it, target qubit, prepare it. Quantum phase estimation algorithm, the CX gate, as we are, I mean, the, we want to get the phase, the eigenvalue, we're going to get the phase, the eigenvalue of the X operator. So we need to do both. Quantum phase estimation algorithm, the C operator quantum gate, C operator quantum gate, and finally the inverse quantum Fourier transform, the inverse quantum Fourier transform. Now we measure. If we get one, that is we get in because here we have the control qubit and the target qubit. Qubit 0, control qubit. Qubit 0, control qubit. Qubit 1, target qubit. Qubit 1, target qubit. As we are getting 1 here, it means that 1 belongs to the minus. So it corresponds to the -1 eigenvalue. If we could get 0 here, it could correspond to the plus eigenvector and it would go to the 1 eigenvalue. Okay, this is for this example in a very simplified way. But let me show another one that is more generalized and it will really help you. I prepare here the encapsulation of a small QPE, okay? That the small QPE, it belongs, is this, all of this, okay? Preparing all the control operator gates. Now, what we are going to do is extracting the theta, the phase of the S operator. So, see here, we apply the S operator, that is a quantum gate, of a single quantum gate, the S operator through the 1, because if we apply to 0, that's nothing. And it includes a global phase. And now what we want to do is this phase. Well, so when we apply the QPU, the quantum phase estimation algorithm over the target qubit 1, what we get in a single qubit, sorry, if we apply the quantum phase estimation algorithm in a single qubit 1, we get this phase. So if we resolve the incognita here, means that theta needs to be 1 divided by 4, a quarter. Okay? All of these operations are applied into single qubit operations. So, S, we have this global phase, and QPU, we have also this global phase, but in that way. So what we want to guess is theta. Okay? And theta needs to be 1 divided by 4, a quarter. Means that all of this, I mean, we know in front, we know up front, we know by hand what the solution should be because this is a theoretical and very, very simple example. If we put here any operator and we put where we don't know the eigenvalue and we put the vector that is in this operator, even it's not diagonalized because this is diagonalized, the quantum phase estimation algorithm would work as well. I think you will see that in the following subject with Alejandro, okay, for the quantum amplitude estimation algorithm, okay? But what I'm trying to say here is I want to show you how the quantum phase estimation algorithm works and how it works, etc., with a simple example that we know the solution beforehand. This is the way how I also program in business. I do a programming, I formulate the problem, I solve it with a very, very easy example so I know the solution. And once I do the solution of this easy example of the programming of the code in 3 different levels, I scale it up and I'm obtaining the solution I was expecting. This is when I scale the problem up and I see for more difficult problems. So here is the same. I'm trying to compute the problem to see that I'm getting the expected result to see how it works. But in a real life, we would got a 1 million quantum computer, 1 million qubits quantum computer with fault tolerant, with all the deep circuit, etc. We could put any matrix we want into the quantum computer. We prepare the target qubit with the vector we want, and we would get the phase of the eigenvalue of this vector. Okay? But let's go for it. Then we have here, and we have this quantum phase estimation circuit. Okay, before we continue, one very important aspect. These are the precision, I mean, as many quantum control gates we want to apply, etc. This is the precision of the solution, but this is also something to consider is that as many operators we add, it increases exponentially, meaning that if we want a precision of 1, we need to apply 3 control quantum gates. If we want a precision of 3, that this is the gate, we need to apply 6 control quantum gates. No, 6, no, more, 7. Because this is 0, 1, and 2. Okay? And this is applied to, as here, to control qubit 0, 0, to control qubit 0, 1, to control qubit 3, etc. of the group number. Okay? So now here we are preparing the quantum phase estimation algorithm, the same that we are doing here for that. So what do we do? Control qubit. We initialize the system, the circuit, all Hadamars, as always. Hadamar is the initialization of the system. Target qubit, bit flip. So we have now the target qubit in the eigenstate we want. Then we have the control quantum gates, and we are having a precision of 3. What does it mean? It means that here it's applied to the first control qubit, here is applied to the second control qubit twice because it increases exponentially. And finally, this is applied to the third control qubit 4 times. This is this. And finally, we apply the inverse quantum Fourier transform algorithm to being able to measure the solution, the phase of the solution into the eigenstate. Okay? We get the counts and we get 0, 1, 0. Now we have this. We applied this, and why now get the counts? But how do we know whether this is the solution or not? Well, first, we need to transform this binary number into a decimal number. Once we transform this binary number into a decimal number, then the solution is solution multiplied by the precision of the control gates. I multiply, no, sorry, divided by the precision of the control gates. And then if we really substitute it, we get the 2 decimal number divided by the precision, we get what 1 divided by 4. That is a quarter, that is the expected theta we wanted. The expected theta we wanted. Okay? Why I really illustrate that such a way? All theoretical quantum algorithms, even in classical computing, you always need a pre-processing and a post-processing of the information. Computing is a task, and you do some computing there, and you do a task. But computing is a task, and you do some computing and you do some task. But but there is always a pre-processing, a post-processing of the information. Even in classical computing, you don't see it. There is always pre-processing and post-processing the information, so you are able to do all of this. So I put that here because in theoretical quantum algorithms, well, and not theoretical ones, you always to do a pre-processing, like managing the data in quantum machine learning, and a post-processing, understanding what these variables belongs to the real solution. That this is the case, for example, we get the counts, we get the disarming number, but then we need to do further post-processing to finally get the theta we expected. And what we get here is this theta over here. Okay, and this is all the quantum phase estimation algorithm and how it works. Any question right here, please? No? Okay. Then there is just one more thing I would like to show you. Okay. Yes, there is just one more thing that I would like to show you. That is, and this is related to the deliverable, okay? The deliverable is going to be this exact exercise, meaning that I'm going to associate you in the deliverable some fractions, some divisions, some numbers, and you will need to do a plot on how the precision of the solution scales while you add more and more control qubits. Okay, that this is exactly the point right here. Now, for example, I'm going to do a more general quantum phase estimation algorithm example. And here what I'm going to put is uh, we want to get this phase factor, 1 divided by 5. Okay? And for that, to have a precision of -3, we need to add 8 qubits. Okay? And see, adding 8 qubits, what a circuit so huge it is. And this is, imagine so huge is this circuit, having 9 qubits because we have 8 control qubits plus 1 target qubit. So see how huge it is. And what I really want to show you is, you see how huge it is, right? Okay. We have this. This is not such big, right? But if we decompose, it was not like that. It was not decompose. Yeah, decompose. Because I need to do before. Okay. Maybe it's because S is an elemental gate. Okay, it's because S is an elemental gate and that's why it does not decrease. It does not increase the number of gates. But if we do that here, I mean, this is a huge circuit, right? So imagine if we do now, even more gates are here. And it should be decomposed in a more layer way. So I just want to illustrate you how a mess. Imagine that we need to run this in a real quantum computer. Being very honest, I didn't experience quantum computers the last 2 years, so it might be some improvement. I don't think so. But the real quantum computer, I'm sorry, but I'm laughing because it cannot execute more than 2 qubits and maybe 4 or 5 gates, quantum gates, nothing else, or 3 qubits maximum. I think it's one. It really depends on the quantum computer, but they cannot really execute in a good performance such things, being very honest. So imagine how far we are to run this circuit in a real quantum computer. It's impossible. But coming back to the point, we have this general fact where we want to get that. In that case is 1 divided by 5 because I prepare that in a general way just to be very similar. Remember, it's those 2 pi theta. So theta is everything going out of 2 pi, and this is 2 pi divided by 5. So it's 1 divided by 5. We create this circuit, we execute it. So when we execute it, we have one number, one binary number that has all the points. And this is a binary number, and I just prepare that so we can translate it. And if we translate it, we get that we get the correct number because 1 divided by 5 is 0.2. So we get the number, but with a precision of -3, as you can see here. But if we, instead of 8 control qubits, for example, we just put 3, the circuit is much smaller, we get less counts, but as you can see, we don't have any type of probability, meaning that we don't get even the solution with 3 control qubits for this phase. We need to increase maybe to 6, we get more, and now here we don't have it. We need to increase that to get even more solutions. 6 to 7, let's see in 7, and now it's where we starting to get that. But it's not till 8 where we can get the solution. And this is exactly the deliverables, students. This is what I want you to do. I want you to, for different types of phases, I want you to run the quantum phase estimation algorithm with the generic form to see from 1, 2, 3, adding more qubits till what is the qubit that you need to add to really get a good precision in the solution. Because otherwise, if you just put 1, 2, you don't get anything. And this is what I really want you to show. And I would say this is all for today because the next one is an exercise that if you want, I can show you again because repetition is the key fact, but it's the same as above. We have the T-gate here. We apply the quantum phase estimation algorithm. And what we got in the plot is 0, 0, 1. That is the one decimal. And then we put the solution. We get the phase we're expecting. And this would be all for today. Questions from your side? No?
Can
Any
I, can
question?
I ask a question about the deliverables, Alberto?
Sure, anything you need. Urbano, please.
So they are
One,
not
one,
in Moodle yet,
sorry,
right?
Urbano. Sorry, Urbano, 1 second. Can you stop sharing the screen? Do you have any questions, students, about that? Or can I stop sharing the screen? Okay, I can stop. Oh, there is a question here. Okay. Good. Tell me, Urbano, sorry. Go ahead.
Oh no, I was just gonna ask how is that? Maybe I already spoke about this, but I was just wondering how the deliverables are gonna be. So we're gonna have notebooks or some kind of questions on Moodle, or how does it work?
Being very honest, I don't know how Alejandro's deliverables works. I saw that they are not yet published. I will ask him, okay, to publish them because their class is already passed, and I will contact him after this class, and I will tell him to put. In my case, the deliverables in my case are going to be always the same. I'm going to give you a PDF where the information is very well structured and is very well defined what I am asking for the solution. And this is what you need to deliver. Please, students, you are here. Don't do whatever you want. There are very clear instructions. I know that you are telling me, yeah, yeah, but it's incredible. No one is doing the instructions. There are very clear instructions of what I'm asking for. Just do that, nothing else. No worries. And when I say very clear instructions, I can give you now an example, even I can show you. Okay. The problem is that I didn't prepare this year yet. That's why, but let me, let me, 1 second. What day is today? 20? 1 second. Mm, mm, mm. Mm, mm, mm. Yeah, I need to prepare for you this year, okay? But this is the students last year. I mean, my deliverables, even in quantum machine learning everywhere, are going to be always all the same. No, it's not running. It's not running. I don't know why. Okay, it's not running. I don't know why. Well, sorry because I cannot show you. But basically, I mean, if you have any questions, you can ask me. It wouldn't be a problem. But basically, my all the deliveries will be a PDF where you will see all the what you need to reply and the answer. For example, all my deliveries is I asked you to answer the Jupyter. For example, in this quantum phase estimation, is answering me with a PDF or Word document answering three questions. One is what is the quantum phase estimation algorithm? Second is plot the number, and three, what are the results? Comment them. This is enough. I mean, I don't need any coding or whatever. If you attach the coding, perfect. So in the future, if you are not comfortable with the mark, it's better to have it. So I have it and I can see it. Perfect. But what I really will be scoring it is the PDF. And all my derivatives is having very, very clear PDFs. I mean, and with very clear instructions. So yeah.
Okay, thank you.
No, you're welcome. Okay, students, any further questions you would like to know? Something else? No? Okay, then thank you very much all. I'm going to stop recording the session.